So welcome everybody to the afternoon session. And our first speaker is Marko Znidaric, who will speak about localized and ballistic eigenstates in counting spin ladders and the Fermi-Hubbard model.
Yes, thank you, Chairman. Thank you to organizers for the invitation. And a good afternoon to everyone who came here for an afternoon nap. It's actually fine, first half of my talk will be sort of an introduction and a bit broader than actual core of the subject that I want to speak about. So if you set your timer like 15 minutes from now, you will be perfectly fine. Anyway, so the result that I want to speak about is I will show you that in a class of models that you can describe as a spin ladder in spin language, or in fermionic language, this would be like a spin full interacting models. That class of models, I will give you details later, is in general chaotic according to standard criteria that people use, but also includes integrable points. In particular, 1D Hubbard model would be also an instance of that class of models. Now, nevertheless, I will show you that one can construct exponentially many eigenstates whose properties are completely different than properties of eigenstates in the rest of the Hilbert space. And so there are those special states. They can be of interest in itself, or they're also important for any possible claims that, for instance, about localization or no localization in such interacting models, or about properties of eigenstates, sort of ETH-like statements. So here's the outline. So first I will describe actually an experiment where a particular case of such a model can be realized. This has been studied in the context of many-body localization. And then the later part, the second part, I will actually speak about the construction itself. It's actually very simple, so it's kind of surprising that, as far as I know, it hasn't been mentioned before. So I will be able to explain you this in like 3 lines, basically. Okay, let us start. So first, one slide really broadly for motivation. So sort of colloquially speaking, we can speak about 2 extreme cases of phases. One I will call thermalizing phase, and you might view this as typically being a quantum chaotic model. So like we expect that most systems will belong to that phase. So system in such a phase has good thermalization properties and so on. Now, we always sort of strive for exact solutions. They're, of course, very hard to come by. But let me mention one case where one can get some exact solutions, and they could put them in this thermalizing phase, namely in a sort of Floquet context. So if you have what is called a random circuit, so a circuit with local transformation, which you pick them randomly from some set of quantum gates. It's time-dependent system, so no conservation law, energy is not conserved, but nevertheless you can ask yourself how fast do you converge to the invariant measure. And this has been studied in quantum information already a number of years ago, and one of the first exact results is about the convergence rate, how fast you converge, or if you want, what is thermalization time. Or in more modern language, this will be called an entanglement speed, how fast you generate entanglement. Or like technically is connected to a so-called 2 design that we heard about in the morning's talk. So you can find more details in the paper. Some of those circuits you can map exactly to a Markovian classical process, whose transition matrix, in turn, can be reduced to a spin chain. And in some cases, those spin chains are integrable, and so you can get exact results for the convergence rate. I will not speak about that, but if someone is interested, we can discuss afterwards. Log, sorry, can you?
In the random circuit, the thermalizing rate.
Right.
What is the function, log or function?
Function of what? Of system length?
System size.
It's polynomial, yeah, indeed, polynomial. So basically it reduces to the calculation of the gap of this Markovian matrix, which in turn is like 1 over L with some prefactor, and you can get even a prefactor exactly. And so there is exact expression. Yeah, feel free to interrupt me at any point. Yeah, if you have a question, just stop me. So second class of systems, sort of, the other extreme case are non-thermalizing phases. They are rare in a sense, and integrable models would be typical representative cases of that. And more recently, much discussed so-called many-body localized phase. Some of the results that I will mention will sort of touch upon that question of whether in a given model you have MBL or not. Okay, okay, these are just two extreme cases. So what a physicist might naturally ask is, what about some phases intermediate between the two? So for instance, you are neither fully, say, chaotic nor fully, I don't know, integrable, yeah, non-thermalizing. And in the last number of years, there have been many studies, many suggestions. Let me mention or briefly overview what has been done so far. So one suggestion, theoretical suggestion, is a case where some degrees of freedom would have different properties than others, in particular with respect to the scaling of entanglement with systems length. So for some, you might have volume law, for others, an area law. This is called quantum disentangled liquid. Then there is a whole bunch of works, mostly numerical, except for those guys here, where motivating point is to ask whether one can have localization or many-body localization, if you want, even without disorder. So in translation invariant system. So whether you can really have localization or not, it's not clear, but what is certain, and you have many works along those lines, is that you can definitely have slow MBL-like dynamics, yeah, up to very long times. And what happens asymptotically, I don't know. So some of those cases are, for instance, you can have dynamical bottlenecks. So somehow your dynamics gets stuck, even though in the equations of motion, in the Hamiltonian itself, you don't have any explicit constraints. Yeah? And in some cases, actually, one can argue that such dynamical bottlenecks will be generic if you start away from some integrable model. Then you can also introduce explicitly some small parameter. A canonical example might be a system where you have light and heavy particles. And so heavy particles will be sort of immobile compared to the light ones, and they can act as a sort of static disorder for light particles. And therefore you can get sort of a MBL-like freeze dynamics up to very long time scales. So this is this case. Here you need really very small parameters to have separation of time scales. Then there are some cases where you can, in a way, sneak in disorder through to initial state. So for instance, imagine that 1 degree of freedom would be again sort of a static one without any real dynamics. Then taking generic initial state for those sort of static degrees of freedom, you can introduce disorder, effectively disorder for dynamic degrees of freedom. There are some works on that. And really, even more recently, among those recent works is where you explicitly have some Hilbert space constraints. So those will be so-called, say, PXP models that you might have heard about. Then second class, so this is mostly numerical, as I mentioned. Second class are exact results about specific eigenstates in some models. Let me mention a few of those works. Probably one of the earliest is by Young, so-called eta pairing states in Hubbard models. Then a bit related are sort of similar looking states in, for instance, AKLT models, or generically spin 1 models, where again, you can get sort of using some ladder operators, you can construct exact eigenstates. And what is common to those eigenstates is that their entanglement is logarithmic in L. And then lastly, if you have some additional non-trivial constraints, for instance, this would be like a dipole moment, then conservation of that guy means that 2 particles cannot get very far apart from each other. So effectively, you get a confinement. common to all those works is that the number of those special states is at most polynomial in the system's length L. In my case, that I will show you in the second part of my talk, the number of those special states will be exponential in L. But still, just to, still sub-leading in the total Hilbert space size, yeah? So they are special. All right, so let me start then with the particular case that belongs to the class that I will more generally discuss later on. It's a 1D Hubbard model, yeah, just hoping you have spin up and spin down particles. There is on-site interaction, and you also can allow for on-site potential, detuning or disorder, whatever way you may want to call it. Such model has been realized in experiments, and I will describe you on next 2 slides how this is done. For now, just pay attention that I will be focusing on a particular case of this on-site potential, namely, this potential value has a cosine shape with irrational beta, so it's quasi-periodic potential, and it's coupled to the charge or density degree of freedom. Yeah? So it's symmetric with respect to exchanging up and down fermions. This will be important and crucial for what I have to say. So in one word, we have interacting spin-full fermions in a quasi-periodic potential, and then question is, do we have localization or not? This will be called many-body localization because we have interaction here. This has been studied numerically, but then also experimentally, and I will spend some time to explain you how those very nice experiments go. I mean, you have probably have heard, or at least seen some of that on some other occasion, but let me nevertheless go quickly through it. So the way it goes is you prepare initial state in that. So this is in particular experiments done in Immanuel's Bloch group in Munich. So here is the reference. So you prepare initial state in an optical lattice where you have sort of dimerized initial state. So every second site is empty. It's called a charge density wave initial state. So say even sites are occupied with either particle having spin up or spin down. Yeah? You don't control this spin occupation, but preparation is such that half of spins is up, half down. Then you let it evolve, and you test ergodicity, or if you want localization or no localization, by looking whether those initially inhomogeneous particles will, after a long time, be equally distributed among all sites. Yeah? So if you are ergodic, then you expect those particles to jump randomly left and right. And so after a long time, you expect equal occupation of every site. Yeah? And you can measure this by so-called charge imbalance. So it's a difference between occupation of even and odd sites. And then you look how this imbalance decays with time. Yeah? If after a long time you see some non-zero value, then you will say, it's non-ergodic, so you say, okay, in this regime I have localization, many-body localization. If it goes to 0, you say, okay, I'm ergodic, yeah, no localization. Now, preparation procedure is the following. So first you cool your atoms, potassium atoms, 2 lowest hyperfine levels are your particle, say. So this cloud of potassium atom is like of order, just to give you a picture of it, it's like 50 microns across. In Z direction, this cloud is very thin, so nothing interesting is happening in the Z direction. All the interesting stuff is in XY direction, which is plotted here. And then you form an optical lattice with, well, in total 6 laser beams, but in this XY plane you have 5 laser beams like that, with 3 different frequencies or wavelengths. The first step is to prepare this charge density wave initial state where even sites are empty, odd sites are occupied. The way you do this is that you turn on first these 2 first lasers, 1064 nanometers and 532. The ratio of the frequencies is 1 to 2. And if power of one laser is much stronger, then you will get this double well sort of potential where you have shallow well, deep well, shallow well, deep well. Yeah? So initially, all your atoms will be in the deep wells, and when you switch off one of the lasers adiabatically, then you end up with every second site being occupied. So this is how you prepare your initial state. Then to make this quasi-periodic potential, you switch on a third laser, if you want, whose wavelength is now, well, sort of incommensurate with the primary frequency. And this then forms this quasi-periodic potential, and then you let it evolve. Your system is this Hubbard model, so on-site repulsion can be tuned using Feshbach resonance. You can also tune the amplitude of that laser simply by cranking up power. Yeah? So you can tune both delta, the amplitude of potential, as well as interaction. You let it evolve for some time, like 50 microseconds. Now to give you a hopping strength is like 0.3 microseconds, so which means that you can evolve it up to like for the 100 hopping units of time, 100 hoppings, or perhaps a bit more. After that, you have dephasing effects and you are not coherent anymore. So you let it evolve for some time, and then you want to measure occupations of even and odd sites. The way you do this is by so-called band mapping technique. So what you do is you again ramp up this green laser adiabatically slowly, so that again you end up with shallow, deep potential. And as you will remember, if you have like a lattice with a basis, one atom in a basis, you will have two bands. Yeah? So by switching on this second laser, you effectively move all atoms on even sides into a higher band. Yeah? So you sort of in a quasi-momentum, you split even and odd sides, and then you just switch on all your trapping and let the particles evolve. And by the time of flight method, you detect how many particles you had in a higher band, in other words, on even side, and how many particles you had on odd sides. Yeah? And this is, just make a photo of it, and this is a picture that you get. So for instance, this blackness represents all particles in the lowest band, meaning all, say, even sides. Yeah? And these two sides, a bit less dark bands, correspond to particles on odd sides, yeah, in the higher band. You just integrate this darkness. And initially, if you make this picture after a very short time, then you see almost all particles are at even sides. Yeah? Right. Well, okay. Like I explained, so you basically, by switching on this second laser, making it a double well, you move all particles at even sides into a higher band. So make a Bravais lattice with the basis, yeah? And so you have two bands, and basically you do it in such a way that you move all particles that were at even sides into a higher band, has higher quasi-momentum, and then essentially you let it evolve. No. Yeah, it's a collective. So this is really, I don't know how technically it's done. It's probably some CCD, you make a picture, one shot, and that's it. Yeah. So by doing that, you get basically one data point in that graph. Yeah? And then you have to repeat the whole procedure for different times. You get one curve, then you change parameters, you get another curve, and so on. Yeah. So sort of very controlled, nice, and complicated procedure. Yeah, it's like a evolution of many decades of AMO physics. But yeah, at the end it works. Yeah. Okay, so you do that, then you vary your parameters, and what you get at the end is a proposed phase diagram. So this is now interaction. On y-axis is the amplitude of that potential. Now let me, and then this is a curve suggested from, based upon experiments, yeah, whether you have this non-zero plateau in the imbalance or not. Let me first tell you what is exactly known about that model. Namely, without interaction, without this guy here, the model is just quadratic. It's the famous Aubry-Andry-Harper model, so, which is also self-dual. So from a point of view of a physicist, everything is known about that model. In particular, if this delta parameter here, is less than 2, then all eigenstates are extended and ballistic. If this delta is larger than 2, all eigenstates are localized. So I said from the point of view of physicists, everything is known, but just as a sort of side remark, there is a whole field in mathematics that studies these so-called almost Schrödinger, almost Mathieu operators, quasi-periodic Schrödinger, where there are also some very interesting questions, also some famous like 10 Martini problems, but I will not go into that. And experimentally, non-interacting model has been already realized in the group of Inguscio in Florence, like 2008. Okay, so this is the phase diagram proposed based on this full interacting model. And now note two things. So first, the imbalance that is measured is this charge imbalance. So for technical reasons, the easiest thing to measure is really density. It's hard experimentally to resolve whether you have spin up or spin down particle. In principle, it's supposedly doable, but no one does it. But the model itself has locally 2 degrees of freedom, right? You have locally charge and spin degree of freedom. So you might immediately ask yourself, okay, so charge degree of freedom behaves like you see here. Yeah? It sort of freezes. What about spin degree of freedom? Yeah, now this question becomes even more sort of natural if you look at the way you put this potential, right? Because the potential, or this order, if you want, is coupled only to the charge. Yeah? So you might justifiably suspect that perhaps spin will behave differently than charge because you put this order only on charge. Even though in a Hubbard model, of course, charge and spin are not decoupled exactly. Okay, so the question, do charge and spin behave the same? And the answer is no. So we did some numerical experiments, sort of analogous to what they do in real experiments. And then if you look at sort of comparable timescale as an experiment, indeed charge looks frozen, so like localized, but if you look at the spin degree of freedom, it just decays. So even on those timescales of order 100 hopping, charge is completely different. It delocalizes. And there is very short, easy answer why this is so. You will believe me that you can express this plateau value with just diagonal elements of the respective operator. For instance, the plateau in the spin imbalance will be given by the diagonal elements of spin operator. Now spin is odd under exchanging up and down particles, whereas Hamiltonian is even. So immediately all diagonal elements are 0, which means in a finite system, the plateau value of this spin is exactly 0. It's one-line calculation. Now, of course, if you pay attention or question to people who are doing exact generalization and very much like eigenstates, question, is this argument okay in the thermodynamic limit? The answer is no, yeah. So this argument, it's not fine in thermodynamic limit because I'm implicitly, immediately, as soon as I write eigenstates, I'm making the incorrect order of limits. Here I'm taking limit time to infinity first, yeah, to be able to eliminate all the off-diagonal elements, and only then L to infinity, which is not the correct thermodynamic limit. Yeah. So in principle, this doesn't tell you anything, yeah. But sort of then there are theoretical arguments that if you have SU2 symmetry, which this Hubbard model does have, that is incompatible with localization. So I think it's fairly certain that indeed spin will delocalize. You can then discuss whether also charge will ultimately delocalize. Probably it will, but it's not clear, fully clear. Yeah.
You mean that even at U very, because here's U equal 1, right?
Yeah.
Even taking it much smaller, still the spin would not localize?
Well...
No, none of them would localize?
Probably, well, okay, that's now a delicate question. I will say a few things about that one. So, okay, the short answer is probably none, although small u is adds additional complication, yeah? It can be a subtle question. So I can say a bit more. about small u behavior in a simpler situation. Namely here, situation is complicated because you have 2 degrees of freedom, right? Charge and spin. Now you might forget that complication and ask yourself, okay, how about spinless fermions in the presence of this quasi-periodic potential, like the one they have in experiment? Yeah? In particular, because as I discussed, so this proposed phase diagram is definitely not fine for spin. Yeah? So you cannot say that you have full MBL because spin is apparently completely different. So you might hope that this phase diagram would be fine for spinless model, right? Because then you don't have these complications with 2 degrees of freedom, because then your disorder really couples to the only degree of freedom that you have, spinless fermions. Then we did numerics, and what you find out at small interactions is that irrespective of from where you start, both from ergodic or localized side, for small interactions you always see diffusion. So it seems that somehow whatever non-interacting physics you have, localized, ballistic, or anomalous, for instance in the Fibonacci model, at small interactions and not too large amplitudes of your potential, you always seem to go to diffusive. So
even at large, I know there is no disorder, but even at large disorder?
Yeah, no, so I actually wanted to immediately, yeah, no. So for not too large lambda, for not too large disorder, yeah. So in principle, the results that you guys have about, yeah, sort of numerically, we can more or less go sort of close-ish to the proposed transition point, so we cannot say anything about that, unfortunately. Yeah.
When you do this reactor versus this Fibonacci model, you basically get similar fits for both?
Yeah, so non-interacting physics is very different. That's why we also compared with the Fibonacci model. But as soon as I switch on interaction, physics seems to be similar. So similar in a sense that in both cases it's diffusion, but the scaling of diffusion constant on the interaction strength is different. Because this will be sort of influenced by the non-interacting limit that you have to approach. All right, so now wake up. Let's go to those special states. So here is now the model in full generality. This is based on a recent work with Tom Yadekola. So you have so now I will phrase everything in spin language instead of fermions, but it's equivalent. So you have 2 legs and hopping along the 2 legs. Yeah? So sigmas are Pauli matrices on the upper leg, taus are Pauli matrices on the lower leg. So pure hopping along the legs, and then on the ranks you can have more general terms. In particular, this delta is now like a Hubbard interaction along that direction. This order is again symmetric with respect to exchanging up and down legs. So this is important. There is Z2 symmetry. And then you can also allow for hopping along the ranks. In spin language, this would be spin flipping hopping. And some important cases of those models. I mean, you can have also clean model without disorder. So I allow for different parameters on different ranks. So there is this index k here. If j is equal to 0, so without this spin flipping hopping, this is just the Hubbard model. So Hubbard model integrable without disorder. But in general, for non-zero j, the model is chaotic. It shows diffusion for sufficiently small disorder. And if you test like level spacing statistics, you see Wigner-Dyson. And now in this class of models, irrespective of the constants, I will construct those invariant states. So, well, okay, let me, before that, just a brief comment on the symmetries. So total magnetization is conserved. So I will discuss transport properties. Then there is crucial Z2 symmetry here. And in the Hubbard limit, you can have, I mean, you have, in addition, SU2 symmetry. But in general, this SU2 symmetry is gone if you switch on also J. So you can have a model with or without SU2 symmetry. It doesn't play a role. And here is the construction. So the way you do it, you go into the rank eigenbasis. And rank eigenbasis is very simple. So my notation is now the upper number is upper leg, lower number, lower leg. So there is a singlet, there is a triplet, and then there is a doublon, so 0, 0, and a holon, 1, 1. Those are eigenstates of a rank part. And also trivially, products of those rank eigenstates on different ranks are eigenstates also of course, total rank part of my Hamiltonian. The important thing is now what does the leg part, so this H parallel, what does it do on the products of those rank eigenstates? And you can easily convince that, for instance, if H parallel acts on TD, like a triplet times doublon, it will just exchange the two. Yeah? So it's just hopping. And similarly for other combinations. So if you have S or T neighboring D or H, those two guys are just exchanged. It's just a hopping. And then another important relation is that H parallel annihilates ST, TS, or HH, or DD. And so you will immediately now see that if I make a state which is just ST, 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 or vice versa, TS, 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 and so on, those two guys are eigenstates of the total Hamiltonian with this particular eigenenergy. So they are kind of inert backgrounds, or if you want, a vacuum. And now I will construct invariant subspaces by putting some excitations on top of those two vacuum states. Here it is. If you insert, for instance, a single doublon in this background, then remembering the rules on the previous page, this doublon will now, under the action of total Hamiltonian, just jump left and right, yeah, to all L different possible positions. Similar thing happens if I insert, for instance, R, some other number of either only doublons or only holons. Also, those guys will just jump around, meaning that they form invariant subspace, and the dynamics on that invariant subspace is that of a free model. And the size of those subspaces is like given by this binomial symbol. The total size is exponential. Yeah? So we have free subspace with on-site energy now being determined by this H per perp, yeah? Which can depend on the site where I have a doublon. And then playing with those constants, I can have either Anderson localization here. If I take delta equal to H, doublons are localized, holos are ballistic, and so on. And taking some quasi-periodic disorder, I can also get any other transport in the subspace, even though in the rest of the Hilbert space, everything is diffusive. Okay, and now last slide before I conclude. So you have exponentially many, but sub leading to the total Hilbert space, which is 4 to the power of L. L is the number of ranks, yeah, which is free. They are everywhere in energy. So I didn't show you that, but they are everywhere. Yeah. Now the relevant question, of course, is considering they are subleading, like measure 0, are they relevant? Yeah. And well, one can argue that at least from experimental point of view, they are very easy to prepare. Yeah. They are just a certain, you should not mix, the sort of bottom line is you should not mix doublons and holons. So you start with the vacuum and then insert just doublons or just holons, and you're fine. So it's not a very complicated thing. And on top of it, it's also stable to small breaking of this Z2 symmetry. Z2 symmetry exchanging upper and lower leg is a crucial thing. And here I break by 4%, and it seems that it's sort of stable, actually better than to the precision of 1 over epsilon that you would naively expect. Okay, and so let me conclude now. So we have large invariant subspaces in otherwise chaotic or special points Hubbard integrable model. Sort of Hubbard-like models, there is Z2 symmetry. So if you remember my remark, one might generally argue that SU2 symmetry or non-abelian symmetry in general is incompatible with many-body localization. Here you see that it's a bit more subtle. So if you have that kind of model, for instance, even with SU2 symmetry, you can have this Anderson localization, localized subspaces. So one has to be a bit careful. You can engineer also any other transport by playing with this quasi-periodicity of your potential. And also, if you would like to have a statement about, I don't know, some properties of eigenstates, for instance, ETH, that would hold for really all eigenstates, at least in that particular model, it doesn't hold. Yeah, so there are exponentially many that violate it. Okay, and lastly, I have a postdoc position, so if you have some student who might be interesting, please forward the announcement. Thank you.
Any question?
Is it possible to understand that mapping one more time?
Yeah, I was a bit quick just to allow for 5 minutes of questions, so now we have time. Yeah, so for instance, I mean, two crucial properties are, for instance, the fact that those two guys are eigenstates, yeah? So, I mean, do you have a particular question? So, for instance, I can walk you through.
Your sigmas and taus,
Uh-huh.
so they lie on.
Ah, right, okay, so let me, yeah. So sigmas are on the upper leg, taus are on the lower leg. Now, my notation is that the upper number here is the eigenvalue of sigma z, and the lower number is eigenvalue of tau z on the lower leg, yeah? So this is like this notation. And so this singlet, for instance, is spin up here, spin down here, minus spin up on the upper spin and the other way around on the lower spin. So this is just the eigenbasis of one rank, those four guys.
You are trying to claim that under H parallel.
Right. And now the claim is that H parallel has very simple dynamics on a specific set of combinations of those guys. If you count the number of these simple relations, it's a bit less than 16 in total. It's like, I don't remember, like 11 of those are simple, yeah? Others are complicated. The complicated ones are those where you mix doublons and holons. And so if you stick with just either doublons or only holons in this inert background, you have simple dynamics that of a free hopping. Where on-site disorder is then determined basically by, where do I have it? Basically by the, well, the eigen energy of H perp, which is then determined just by the location of your doublon or holons. So I can explain you more. Yeah.
So you raised the question of how your theory goes with between quotes proofs of no MBL in SU2 systems.
Yeah.
But if I remember correctly, there is the argument which is basically mathematical by Vasseur that says that there cannot be Lyons, right, in SU2. But that's consistent with what you have because you don't have Lyons.
Yeah, it's sort of inconsistent with a bit more hand-waving argument, which is very natural and in general, I think, correct, yeah, that you say that if you have non-abelian symmetry, you will have extensive degeneracies, and then somehow you expect sort of break up immediately when you switch on.
Right, but those more heuristic arguments, I think they are meant to apply for generic models, isn't it?
Right, yeah.
So,
I mean, if you correctly understand with caveats all those statements, there is no contradiction. But if you are sort of naively understand them in incorrect way, then you're in trouble, yeah.
Thanks.
Okay, so good.
This is much more complicated than my question.
Yeah, these mics are hard to handle, I noticed.
So in those states which are localized in your model, these 2 to the L or some states, so would all of them have area law because they are localized?
Yeah, good question. So now it depends because I can play with this disorder, yeah? So for instance, if I would take, I can pick any delta, any HK, and also hopping along the ranks could be also picked up. So now if I have localization, like Anderson localization, yes, then actually you will have a fixed entanglement. Yeah. If you have something else, you will also have, in particular, if I play with quasi-periodic HK, yeah, then I can have all this Fibonacci, Andreobriand, and blah, blah stuff. I can engineer basically whatever you want.
But anyway, there's only one particle going around.
Not necessarily. You can include any number of doublons. So like, half of the guys can be doublons and half ST-ST background.
Oh, that's what I missed. So doublons, so
Yeah.
that's like a hardcore particle.
Indeed, indeed. So the important thing about that is, you see, if two doublons meet, they're just annihilated. Or two holons. You have symmetry with respect to doublons and holons, of course.
Any other? So I have one small. So in your first model, in your phase diagram, there was a whole region which was nor green nor this diagram.
This one?
Yes. What is that mean? Is that the place where?
The experimental one? Yeah. Okay. So okay. This is from the science paper by Bloch group. Yeah, and this hashed or whatever, this region is meant to be in the experiment. They have also certain probability to have doublons on sides. Yeah. And so now this, without doublons, a proposed phase diagram is this curve, full line, and with certain fraction of doublons, it's here. Yeah. So if you have many doublons, then you would be here, right? You would go down there.
So it strongly enhances the localization.
Indeed, yeah. And in experiments, they have, I don't know, what fraction of doublons, which is supposed to be this dotted line somewhere in between here. Yeah. So the more doublons you have, yeah, the enhances localized region. Indeed, true.
Anything else? Okay. So thanks a lot. Yeah.